Now I'd like to talk about how we would derive our heat diffusion equation using Cartesian coordinates. So to model this, I am going to draw a cube. And we are going to have a flow coming through the left side and leaving on the right side in the x direction. And we are also going to have our z direction pointing upwards. So I'm going to draw out our coordinates. We said that moving from left to right is x, going up is z, which means by the right-hand rule, our y-coordinate must be going into the page. So we're going to have some position here, x, and there's going to be some thickness along here that we are going to represent as dx. And the same can be said for dy and dz. This means that our volume for this cube is going to be dx times dy times dz. And we want to start thinking about what the rate of change of energy storage would be inside of this cube. So that equation is going to look like the density times the heat capacity times the volume times the temperature. And we want this to be a rate of change. So in order to do that, we're going to have the density times the heat capacity times the change in temperature with respect to time multiplied by our volume, which we just said was dx times dy times dz. We're also going to have a rate of change of energy generation. So that is going to be labeled as E gen. And this is going to be a heat flow per volume. So we have to multiply this rate of change of energy generation by our volume, which is dx, dy, and dz. And we're also going to have heat flowing through this in both the x, y, and z direction. So right here, we're going to have heat flow at our at our x point. And then later on, we're going to have another heat flow at this x plus dx because we have to take into account this thickness and that we're at a different point. So our net heat flow in just the x direction is going to be the heat entering minus the heat leaving. So we're going to have qx minus qx plus dx, the heat flow at our later position. Qx plus dx can be represented using Taylor series approximations. So this is approximately the heat flow at our position x plus the derivative of the heat flow at that point with respect to x multiplied by how far we went, dx. Now, if we plug this back into our net heat flow equation, we're going to have qx minus qx plus the derivative, the heat flow at x with respect to x multiplied by how far we went, dx. Now evaluating this, we're going to have our qx terms to cancel, and we're left with negative the derivative of the heat flow at that point x with respect to x multiplied by dx. And now you'll notice we have a qx term. We can actually expand on that as that can be written out as Fourier's law. So it's going to be negative qx is equal to negative our thermal conductivity multiplied by the area multiplied by the change in temperature with respect to x. Our area in this case is going to be dy times dz. So we can substitute that in. The heat flow at x is going to be the negative thermal conductivity multiplied by dy dz multiplied by the change in temperature with respect to x. Now we can substitute that in up here. We're going to have negative the derivative with respect to x multiplied by the negative thermal conductivity multiplied by dy times dz times the derivative of the temperature with respect to x times dx. And you'll notice that we can take out this dy dz term right here because that is not dependent on x. And also our negatives cancel. So we're going to have the derivative with respect to x multiplied by the thermal conductivity times the change in temperature with respect to x multiplied by dx, dy, dz. Now to put all of this together as if we're only focusing on one dimension, which is the x, we're going to say that the rate of change of energy storage is equal to the rate of change of energy generation per volume plus the net heat flow in our x direction. So if we put those together, we're going to have the density times the heat capacity multiplied by the change in temperature with respect to time is equal to the heat flow, the rate of change of heat flow per volume multiplied, sorry, this should be multiplied by volume as well. So dx, dy, dz, which is equal to our rate of change of energy generation, which we said was q dot multiplied by our volume, dx, dy, dz, plus our q net of x, which we just found. So this is going to be plus the derivative with respect to x multiplied by the thermal conductivity times the change in temperature with respect to x multiplied by dx, dy, dz. Now, if we want to isolate our derivative of temperature with respect to time, we can first start off by dividing by our differential volume. So we're going to divide that out. All of those will cancel, and we're going to be left with rho c times the derivative of the temperature with respect to time is equal to q dot plus our derivative with respect to x multiplied by our thermal conductivity times the change in temperature with respect to x. And to make our lives easy, we're going to say that our thermal conductivity does not depend on x. Therefore, we can take it out of our equation. If we take that out of our equation and divide both sides by rho c, we're going to find that we have the derivative of temperature with respect to time is equal to alpha, k divided by rho c, multiplied by the second derivative of temperature with respect to x, plus the energy generation rate divided by our density and our heat capacity. So that is the 1D heat diffusion equation using Cartesian coordinates. Later, we're going to incorporate both y and z, but for this purpose, I wanted to do that. And now we're going to jump into an example where, let's say we have no energy generation, or sorry, no energy storage rate, but we do have energy generation rate. So that would look like 0 if we cancel out our energy storage is equal to alpha, which I am now going to change back into k divided by rho c, and you'll see why in a second, multiplied by the second derivative of temperature with respect to x, plus our energy generation rate divided by density times heat capacity. We can take out our density and heat capacity term, so we'll be left with 0 is equal to our thermal conductivity multiplied by our second derivative of temperature with respect to x, plus our energy generation rate. Now, if you solve this, you'll see that our second derivative of temperature with respect to x is a constant. This means that our first derivative is linear, and this means that our t function is a parabola. And the reason I'm pointing this out is because within our next example, we're going to have to draw out a temperature profile, and I just wanted to show you why it is a parabola. Using what we just learned, I want to take an example of this material where one side of this material is perfectly insulated. This material has some sort of volumetric energy generation rate Q dot, some thickness L, some thermal conductivity K, and some area A. Now we can say that the volumetric energy generation rate is equal to the amount of heat that is leaving through the uninsulated side. So we're going to take the volumetric energy generation rate and we have to multiply it by the volume. And in this case, that's going to be the thickness L multiplied by the area, which is equal to the heat leaving on the uninsulated side, which we can find by Fourier's law. So Fourier's law is negative the thermal conductivity multiplied by the area multiplied by the change in temperature with respect to x. Now, if we make this position over on the left side, x is equal to 0, and our increasing x values going from left to right, this means that our volumetric energy generation rate must be negative. So if we solve for our gradient, the derivative of t with respect to x, our negative signs cancel as well as our areas, and we're left with the derivative of temperature with respect to x, evaluated at x is equal to 0, is equal to the volumetric energy generation rate times the length divided by the thermal conductivity. Now, drawing out a temperature profile for this, it's going to look something like this. So this is going to be our insulated side, and we know that the temperature gradient for a side that is perfectly insulated is going to be 0. So we're going to have these flat lines all across here. From the other side, the uninsulated side, our temperature profile is going to look something like this. Just like I had said previously, it is a parabola. Even though we don't have both sides of the parabola, it is still a parabola. And the reason our slope is increasing is because if you just take a look at the right side of our temperature profile, we can see that we only have half as much heat that is being generated. Therefore, only half as much has to leave, so our slope is not going to be high. Whereas if we look at the total picture, all of the heat is being generated and all of it has to leave via conduction. Therefore, our slope has to be greater. Now, going back to our Cartesian coordinate problem, I want to start working on our other directions, our y and z directions as well. So we left off finding the net heat flow through the x direction. So now I want to do the net heat flow through our y direction. So similarly as before, and you'll find all of these kind of follow the same pattern, we're going to have the heat flowing through our y position minus the heat flowing at our y position plus some later y position. Now we're going to use Taylor series approximations again, and we'll find that qy plus dy is approximately negative the derivative of the heat flow at position y with respect to y multiplied by the distance we moved dy. Now we can plug in Fourier's law again. So this is going to be negative ka dt over dy. Our area this time is going to be dx dz. So if we plug that in, we're going to have the derivative with respect to y multiplied by the thermal conductivity K times our area dx dz multiplied by the change in temperature with respect to y multiplied by dy. Once again, we can take out dx and dz as those are not dependent on y. So we're going to have the derivative with respect to y multiplied by the thermal conductivity times the change in temperature with respect to y multiplied by dx, dy, dz. The same is going to go for our x direction. So the net heat flow in our x direction is going to equal the heat flowing at some position x minus the heat flowing at some later position x. Sorry, this should be z, not x. Equals the heat flowing at some position z plus the heat flowing at some later position z plus dz. Once again, we're going to use Taylor's series approximations. We're going to find that qz plus dz is equal to negative the derivative of the heat flowing at position z with respect to z multiplied by how far we moved, dz. We're going to plug in Fourier's law. And this time our area is going to be dx dy. So if we plug that in, we're going to have that the derivative with respect to z multiplied by the thermal conductivity times dx dy times the derivative with respect to z multiplied by dz. Again, we can take out dy and dx because those are not dependent on z. So we're going to have that the derivative with respect to z multiplied by the thermal conductivity times the derivative of temperature with respect to z multiplied by dx dy dz is the net heat flow in our z direction. So now we can put this all together just like we did before, because we said that the rate of change of energy storage is equal to the rate of change of energy generation plus our net heat flows. So our rate of change of energy storage was our density times our heat capacity times our change in temperature with respect to time multiplied by our volume dx, dy, dz is equal to all of our net heat flows, which is starting off with x. It was the derivative with respect to x multiplied by the thermal conductivity and the change in temperature with respect to x multiplied by dx, dy, and dz. For the y direction, it was the derivative with respect to y multiplied by the thermal conductivity multiplied by the change in temperature with respect to y multiplied by dx, dy, dz, plus the derivative with respect to z multiplied by the thermal conductivity and the rate of change of temperature with the derivative of temperature with respect to z multiplied by dx, dy, and dz. And we can't forget about our energy generation term. That was q dot multiplied by our volume dx, dy, dz. And if we want to isolate our derivative of temperature with respect to time, we can first start by dividing out by our volume, because each of these terms have our volume in it, so we can simply divide those out. We can also take out our thermal conductivity term, because we can say that that is constant and not changing whether it's x, y, or z. So if we take those out and we divide by row C, we're left with the derivative of temperature with respect to time is equal to alpha, our thermal conductivity, multiplied by the second derivative of temperature with respect to x, plus the second derivative of temperature with respect to y, plus the second derivative of temperature with respect to z, plus our energy generation rate term divided by our density and our heat capacity. And that is the heat diffusion equation working with 3D, 3 coordinates. Now I want to take our heat diffusion equation that we just derived using Cartesian coordinates, and this time I want to model it using finite differencing, but only in 2D with no energy generation and at steady state. So to simplify our equation, for now I am going to keep our derivative of temperature with time in, just for now. This is going to be equal to alpha multiplied by the second derivative of our temperature with respect to x, plus the second derivative of temperature with respect to y. Once again, we're ignoring our z coordinate and we're also ignoring our energy generation. So we're going to say that we have this big block, okay? We're going to have an increasing x direction from left to right and increasing y direction from down to up. Okay. So now we're going to say that we have different temperatures on all 4 of these sides. So over on this left side, we're going to have a temperature of 100 degrees Celsius. On the right, we're going to have a temperature of 200 degrees Celsius. On the bottom, we're going to have a temperature of 250 degrees Celsius. And on the top, we're going to have a temperature of 310 degrees Celsius. And each one of these blocks has their own specific address. They're each going to have some sort of change in x position that we'll note as delta x, and some sort of change in y position we'll note as delta y. And just like we did before in homework 1, we're going to have to use counters for these. We're going to need a counter now for x and y as well as our time. So for x, our position at x can be noted as our counter for x, I, multiplied by delta x, this change in position. Similarly for y, our counter is going to be j multiplied by delta y. And then for our time, we're going to have a counter of n multiplied by some delta t. And just like I said before, each one of these little squares has their own address. So we're going to have to model the different temperatures within each of these. So let's say that this block is going to be our starting position. We're going to have our temperature at our position I, j. If we move to the right of this, we're going to have a temperature at our position I plus 1 at our same vertical position j. If we move to the left, we're going to have our temperature at I minus 1, because we're to the left, at our same vertical position j. Going above, we're going to be at the same horizontal position, but this time we're 1 above our block. And moving down, we're going to be at our same horizontal position, except at this time 1 below from where we were. So now if we want to model the left side of our equation, we can write that out as the temperature at our position at a later time n plus 1 minus the temperature at our position at the current time n divided by delta t. We can then start to write out the rest of our equation. So we're going to keep our alpha term. That's going to be constant. But we're going to have new x and y terms. So starting off with x, we are going to go from the temperature to the right of us at our time n minus the temperature at our position divided by a delta x minus the temperature at our time n at our position minus the temperature to the left of us at our time n divided by delta x, this change in x position. And this is all going to be divided by a delta x because remember, we're working with the second derivative. Okay, then we're going to move on to our y position. So we're going to have plus, now our y positions, we're going to have the temperature at our time n above us minus the temperature at our position divided by a change in our vertical position, delta y, minus the temperature at our position minus the temperature below us divided by a change in our vertical position, delta y. And just like in our x, we're going to have to divide this by a delta y because we are dealing with the second derivative. Now this is our very, very long equation that we have. And to simplify this, I'm going to say that our delta x is equal to our delta y, which we're just going to make as delta. So if we kind of start to write this out, we can have the same expression on the left side equal to our alpha still, multiplied by the temperature to the right of us plus the temperature to the left of us plus the temperature above us plus the temperature below us minus 4 times the temperature at our position at the current time n. And this is all being divided by a delta squared. And like I said before, we are dealing with steady state. So now I am going to cancel this out. We can move our alpha term over as well as our delta squared term over to cancel them. Then we're going to be left with the temperature at our position. And if we assume that this is after a long time, we don't need to include our n's anymore for our counters. So we can have the temperature at our position is equal to the temperature to the right of us plus the temperature to the left of us plus the temperature above us plus the temperature below us, all divided by 4. And now I'm here in Excel. Okay, so now I want to model our finite differencing equation that we just found in Excel. And so over here, I'm going to define our formulas. We had a temperature on the left side of our grid, a temperature on the right side of our grid, a temperature at the top of our grid, and a temperature at the bottom of our grid. The temperature on the left side was 100 degrees Celsius. On the right, it was 200 degrees Celsius. On the top, it was 310 degrees Celsius. And on the bottom, it was 250 degrees Celsius. I'm going to turn these into formulas. And we're going to start building our grid. So over here, we're going to have this as the temperature on the left side. And we're going to drag that down about 20-ish. And then on top, this will be the temperature at the top. Drag this over some. And over here, we'll have the temperature at the right side of the grid. And then lastly, the temperature at the bottom. And now, in order to fill in the rest of the grid, all we need to do is plug in our equation that we found. So that equation was that the temperature to the right of us plus the temperature to the left of us plus the temperature above us plus the temperature below us divided by 4 gave us the temperature at our specific position. So we'll hit enter. And then we'll just drag this down and then drag this over. And there we go. We filled in our grid with all of our different temperatures depending on what position we are at.